Let's have a look at part B of this question. So we have to answer the questions for model 2. We gotta interpret the coefficients, we have to compute the regression standard error and the R-square value. So first of all, let's have a look at model 2 and see what's happening here. We have a constant and we have 4 independent variables. So let's write down this model. Again, the dependent variable is the baby weight, so we are regressing the baby weight. We are predicting values for the baby weight based on a coefficient which is minus 1.832 plus 0.010 multiplied with the value of the gestation, so the predicted value of the gestation, plus 0.001 times the age of the mother, plus 0.014 multiplied with the height of the mother, so height of the mother, plus 0.003 multiplied with the weight of the mother, so multiplied with the weight. So let's interpret every coefficient. Let's start with the constant one. So what would be the constant term? The constant term would be the value of the birth weight if gestation is 0, age is 0, height is 0, and the weight of the mother is 0. Now, none of this can be 0. None of this. Like, it doesn't make sense to have 0 age or 0 height or 0 weight, 0 days of pregnancy. So this makes no sense. There is no need to interpret the constant coefficient. Now let's work with the actual coefficients of the variables. So for instance, 0.010. Whenever we interpret coefficients, the first step is to see whether they are significant. 0.010, we are checking the significance level over here to see if they are less than the significance level that we allow. So this is the p-value of the coefficients, meaning this is the probability that the coefficients that we found in our regression line happened by chance. And if that probability is really low, it has to be less than significance level in our regression that we allow, and that's usually 5%. If nothing is told to us about the significance level, we assume it to be the 5%. That's usually the norm. If that probability that this coefficient we found happened to be by chance is really low, then it most likely did not happen by chance. It just means that the coefficient is significant. It actually has an effect on the birth weight, and that's how we interpret this. The probability of this happening by chance is pretty much 0, so that clearly did not happen by chance, meaning we can say that this is a significant coefficient, a significant effect. How do we interpret this significant effect? Well, by taking the relationship between the effect of gestation on the birth weight. So we have that if gestation increases by 1 unit, and that unit is measured in days, so if gestation increases by 1 day, the birth weight of the child increases by 0.010 times 1 unit, which is the kilogram in this case, because we can see the birth weight is measured in kilograms, which is the same as 10 grams. So 1 more day in pregnancy, 10 more grams for the birth weight of the child on average. This is on average, not for every child, because remember, we always have specific factors for every mother and for every child that's going to affect the different birth weight, genetics, lifestyle of mother, etc. Now let's have a look at the next one. Same method. We have a look at the age, that's the next variable. We have a look at the coefficient, 0.001, but we check the significance level. The probability that it happened by chance is 76.6%. That's really high. It most likely happened by chance. So this coefficient, this variable, has no effect, no significance. It's an insignificant effect of age on birth weight, so there's no need to say anything about it. It just happened by chance to be in this regression. Let's have a look at height. That's going to be our next variable, our next effect. The effect of height on birth weight, 0.014. Again, the probability of this happening by chance is 0, so it definitely did not happen, or not definitely, but most likely did not happen by chance, meaning it is a significant effect of height on the baby weight. What does that mean? Well, if height increases by 1 unit, and what is the unit for height? The height is of mothers in centimeters, so if height increases by 1 centimeter, then the birth weight of the child increases by 0.014 times 1 unit, and the unit of birth weight is kilograms, so that's the same as 14 grams. 1 more centimeter in height on average leads to 14 more grams in the birth weight of children. That's how we interpret it. And now the last coefficient would be this one, the weight of the mother. This is the effect. But then the significance level over here, again, tells us that this most likely happened by chance. That's a 9.3% probability that we found this effect in the regression by chance. If we take other samples of other mothers and children, we will most likely not find such an effect. So this is not significant. No significance, so no need to interpret it. Okay, so that's how we discuss the coefficients, the effects, the significance. What matters now is to find out the standard error of the regression. So we go to our table over here, the ANOVA table that shows us the variation, and we need to work with the variation of the residuals, because the standard error, let's write it here below, the standard error is gonna give us, so the standard error is a measure of the spread of the residuals, or how much. So if we draw it like over here real quick, if we would have a regression, just understand it a bit what it means. This would be our regression line around these values, around such values. The standard error of the regression is going to show us how much on average these green dots deviate around the purple line, the regression line. That's going to be the measure in the standard error. So standard error of the regression is the square root of the variation of the residuals. Now first step is to find out the variation of the residuals. And the variation of the residuals we refer to the average variation. So the variation of the residual is the sum of square differences of the residuals relative to the n minus p minus 1. So we divide by the degrees of freedom to find out how much it varies on average. The sum of squared of the residuals in the model is 144.961, because we're looking at model 2. So that's 144.961 divided by the number of observations. Recall that we have 715 observations minus the number of parameters. That's the number of independent explanatory variables in the model, which is 1, 2, 3, 4 explanatory variables. So minus 4 and then minus 1. And if we work out the math over here, let me go here below to make some more space. If we work out the math over here, this variation, this average variation of the residuals is going to be equal to 0.204. Now, to find out the standard error, we just take the square root of that. So the standard error of the regression in model 2 is going to be the square root of 0.204, which is equal to 0.45. How do we interpret the 0.45? Well, that's 0.45 kilograms, because that is the unit of the dependent variable. Recall, this is the measure of how the actual values, the actual birth weight values deviate on average around the regression line. So it deviates around the regression line on average by 0.45 kilograms, or by 450 grams. So it could be above or below the regression line by 0.45 kilograms on average. It's not going to happen for every observations, but on average. That's the idea. Hope this makes sense. And one last thing, the r square. So what's the r square of this model? Well, recall, the r square is just going to be a ratio of the variation explained by the model, by the regression, relative to the total variation. So we'll just take the ratio of 29.248 relative to 174.209. So let's do it over here below, keeping the table visible. R square would be the ratio of the sum of square differences, the variation explained by the regression. And by the way, this could be confusing because oftentimes they might have different notations for the variation of the regression, the variation of the residuals. You see, residuals is with an R, regression is with an R. I think it's wiser to just note the residuals with SSE, which is the error term. You could associate it with the error term and keep the R for the regression so that you don't get confused. So SSR relative to the total variation, and if we take the values from the model as we said, that's the ratio of 29.248 relative to 174.209, which is the total, and that gives us a value of 0.17 if we round it up, meaning it's 17%, which tells us that 17% of the variation in the birth weight of the children in this sample is explained by the fact that we have different values for the gestation, age of the mother, height of the mother, and weight of the mother. So the model, these 4 variables, explain 17% of the variation of why the birth weights of those children differ from each other. Hope this makes sense, and we are done.